Okay, so hopefully you made that prediction. Now we're gonna see what actually happens. So let's watch. Drops it, comes right to rest. So that is a really interesting situation. That's kind of really similar to what we saw in the copper tube, but it's still a really interesting situation that we're going to want to look at and examine. So when we're looking at this, what we have to look at it through is this lens of Lenz's law. So Lenz's law is what we were looking at last time. We're just going to define it a little bit further and think about the direction of things. But so we said that Lenz's law is this idea that current is induced in a loop of wire when the magnetic flux through that loop changes, and we really need this flux to change. So last time we defined flux as that symbol, that like phi, where we said that flux is really just this flow of magnetic field that is passing through a loop of wire. So really just how much magnetic field do we have flowing through this loop of wire? And we said last time that we can change the amount of flux if we change the actual amount of magnetic field that's going through the loop, if we change the area, so if we change that rotation or the direction, that's not the right, orientation. If we change the orientation of the way that that loop is, and if we change actually like the angle, that can also change it, right? We said last time with this the scissors, if I change it, it's going to affect how much is actually going through it. And then we say we can also have the loop move into or out of our magnetic field. So we can physically, again, if this is my loop of wire, I can physically move where it is along this magnetic field. And so what we're saying is the current that is induced creates its own magnetic field, right? We said that current going through a wire is going to create a magnetic field. And so let me take a step back. So we said, okay, current's going to be induced when we change the magnetic flux. And then if current is induced, we know that current creates its own magnetic field. So current is going to have its own magnetic field, and the magnetic field induced is going to oppose the change in flux. That's really this Lenz's law. And that's confusing. I wrote what because it's like that doesn't make any sense. So let me say it one more time, and then we'll look at what that actually means. But so the magnetic field induced opposes the flux change. Okay, let's look at what that means. So pretty much what it boils down to this idea that nature is going to hate change. Nature is not going to like change. Maybe you guys can kind of sympathize with that right now. I don't like this change of being in this e-learning. We don't like change. We like our routines. We like what we're used to. So what we're going to say is the induced current will try to make up for the missing magnetic field. So we said that this induced current comes about when we have a change in magnetic field. So the induced current is going to go around and try to make up for this missing magnetic field, this change in magnetic field. So just really quick, we have that equation for flux where we said it's the magnetic field and then the area. So we want to look and see, okay, if this flux is changing, our loop of wire is going to try to make up for it. So I've drawn out these pictures and hopefully they'll be helpful. But so what we have in this first case is I have this loop of wire that's moving through this magnetic field with this velocity v. And we're just going to say it's a constant velocity. It's going to make it a little bit easier for us. So we have this magnetic field that is going into the page and this loop of wire that is going to the right. So right now this loop of wire doesn't have any magnetic field going through it. It doesn't have any flux. So right now when we move it around, if we move it over here, it won't really induce any magnetic field because right now there is no, or induce any current. Because right now there's no magnetic field, so it won't induce any current. But if we move it inside here, we have changed the amount of flux. We have changed the amount of magnetic field within that area of our loop of wire. So we know that a current is going to become induced in there. And we know that nature is going to oppose that. Before, nature was like, hey, I didn't have any magnetic field in there. And what it's going to do is it's going to induce a current in such a way that it will no longer have that magnetic field in there. It's going to try to get rid of that magnetic field in a way. That's how we can think about this. It wants to go back to how it was. So it wants to go back to a situation where there was no magnetic field. Now it has a magnetic field into the page. So it's going to create a magnetic field out of the page to oppose that. So if we're thinking about, we know it's going to create a current. We talked about that on Friday. So the direction of the current is going to be in such a way that we make a magnetic field that is getting us back to how we were, opposing that change in flux. So before we had magnetic field into the page. Now what we're going to do is create a current in our wire. We're going to induce a current in that wire. And that current in the wire is going to travel in such a direction that it is opposing that into the page magnetic field. So it's creating this out of the page magnetic field. So we can kind of think about, oh, now there's not really magnetic field in there. It's canceling out, it's opposing it. It won't fully cancel out, but it's trying to get us back to normal. So it's opposing that change. So we see if we use our second right-hand rule, our thumb, if we're pointing it up or to the right or up, anytime we're within that current of wire or that coil of wire, we're creating a magnetic field towards us out of the page. So it's going to oppose that. All right, then let's go a little bit further. So now we're fully in the magnetic field. We've created that current. But now if we move on a little bit further, we still won't have any flux created or any current induced because our flux didn't change. We had, to simplify it, two pieces of magnetic field, right? We have two of those X's. And in this case, we also have two of the X's, and we're moving at this constant speed. So in this case, we didn't change our magnetic field and we didn't change our area. So we don't have any induced current. Now if we move out, well, before we had two, to simplify it, before we had two magnetic fields, and now we only have one. So what our coil of wire is going to do is it is going to induce a current again because we had this change in flux. We had this change in our magnetic field within our area. So it's going to induce a current in such a way that we can have a magnetic field that is pointing into the page, just like we had before. Before we had two, right? All these places we had two magnetic fields. Now we only have one. But nature got used to how we were. It doesn't like that change. So it's going to induce a magnetic field, induce a current that will create a magnetic field that is going to compensate for that missing flux. So in this case, we're going to get a current that is going clockwise. If we have our current, our second right-hand rule, at all of these positions, no matter which way we hold our hand, when we're within that loop of wire, we have a magnetic field, our fingers pointing into the page. And now if we want to analyze the spatula thing, it's a little bit tricky, but it gets a little bit easier. So right now we see on that spatula, it doesn't have any magnetic field. It's not magnetic. It's not within this magnet. This is kind of a crappy, it's kind of a bad drawing, but this is like the magnet that we're looking at. So we have the spatula, and right up here it has no magnetic field because it's just an aluminum spatula. And then if we're kind of looking at the side view, so if it's coming down in there, now it's entering this magnetic field. And it says, well, before I didn't have any magnetic field. Now if we're looking back in that first view, before I didn't have any magnetic field, but now I do have a magnetic field that is pointing out of the page, and I don't like that. I want to do something to get me back to normal. So what it's going to do is it's going to induce a current, in this case, in the counterclockwise direction, so that, oh no, I think I drew that wrong. Yeah, I drew that wrong, sorry. It should be the other way. It should be clockwise, right? Yeah, it should be clockwise. Sorry about that. So I drew the current the wrong way, but it should be clockwise in such a way that the induced magnetic field, sorry about that. So I changed that really quick. But so it's going to be in this clockwise direction so that everywhere we're looking at, we are inducing a magnetic field that is into the page to try to oppose that. And what's a little bit weird is that we don't have a defined loop of wire here. We just kind of have this slab of metal. So what we create is this thing, you don't have to know about it, but it's just kind of interesting, this thing called an eddy current, which is kind of a little loop of current that is being induced. It's going around because it needs to make this magnetic field to oppose it, but there's no really defined path for it, so it's just kind of these little loops, these little like whirlpools or an eddy. If you're familiar with the rivers, I think that's a river term. It's kind of like a little swirl in a river. but who cares? So it's just kind of, it's creating this eddy current, this current that's flowing around to oppose this magnetic field, to oppose this changing magnetic field. And one thing that's kind of cool too is this is one way that we can kind of look at this conservation of energy. The pendulum, or that spatula, it had this potential energy, and as it moved down, it stopped. And usually we're used to it going from potential to kinetic to kinetic to potential, and it keeps on going back and forth, and we have this nice, perfect or ideal conservation of energy. In this case, we're saying, well, we have this potential, it went to the kinetic, and now all of our energy is gone. We can say that our energy is going into this current. It's going into creating this magnetic field. And we can say that's kind of like stored in the field. And also we have this potential that's created. We create this EMF that we talked about on Friday. That is another way to account for our energy. So then last couple things. This isn't super important, but I just found this video. Again, you have these slides, so you can look at it. But so this company is kind of, I don't know, they're talking about how they use Lenz's law on a daily basis in their inventions to either kind of repel you down if you're doing rock climbing, or if you are just jumping off this thing for some reason, because I don't know, that doesn't look like fun, but to each their own. But so in this case they're saying, hey, we have this non-metallic metal, and then what we can do is through induction, I'll let you do whatever. This part. So it's creating this current that's opposing the magnetic field. Cool, cool, cool. So this current here is creating the magnetic field. And really the part that I thought was interesting was over here how they say they do it. They kind of have this continual, these are the aluminum pieces, they're spinning within that magnetic field, and you constantly have this magnetic braking, just like we saw in that spatula, except for it's kind of happening at a little bit of a more constant rate. I just thought it was kind of a cool application for it. But there's a lot more cool applications for it, like maglev trains are also very neat, but I couldn't find a good video about that. So I'm going to stop this video here, and then we'll do a quick practice question, and then we'll be done for the day. I'll give you some practice questions to try, but not too many, and then we're good to go.